Hello student, we are studying our course that is the physics of semiconductor devices, and in that we are studying our fourth module that is metal and metal insulated semiconductor devices, and we are at the end of this module or this chapter, because in our previous videos we have covered all the topics of this chapter except one topic, that is the expression for the space charge for the MIS diode. So in this video we have to discuss about this, but in our previous video we have discussed about the MIS diode, that is a metal insulator semiconductor diode, and in that we have covered the how the metal insulator semiconductor diode is constructed. That means it is a three layer device, and it is constructed with the help of semiconductor, insulator and metal. And when we brought these three materials in contact with each other, then how band bending takes place, and how the formation of the deflection region, and how there is a transport of the charge carriers or there is no transportation of charge carrier. All those things we have covered in our previous video. Now in this video we have to discuss about the expression for the phase charge region for the MIS diode, or the surface phase charge region for the ideal MIS diode. First we have to discuss about the surface states. So let's see surface states. We know that at the boundary of the semiconductor crystalline structure is get disturbed. This causes a creation of the interfacial states which acts as electron traps. These states are known as the surface states. Before going through this definition in detail, we consider, suppose we know that in a crystal there are generally two types of the crystal, that is a single crystal and the polycrystal. In a single crystal there is only one crystal, but in a polycrystal there are number of crystals, that is 1 and 2nd and 3rd and up to so on. These are the different crystals are bound to each other, and these crystals are bound with the help of the boundaries of that crystal. So there is a formation of the boundary, and due to that boundary the overall structure of the crystal get disturbed. That means if we consider the amorphous crystal, then in amorphous crystal the arrangement is irregular. So in a polycrystalline is again same condition, the arrangement is irregular. That means there is a disturbance in the arrangement at the boundary. Suppose here we take the semiconductor crystal. In a semiconductor crystal the condition is the same. At the boundary the structure get disturbed. This causes creation of interfacial states, and due to the disturbance in that structure there is a formation of the interfacial states, and which acts as electron traps. That means these states acts as electron traps, and these states are known as the surface states. So this is all about the surface states. Now we have to discuss about the surface phase charge region for ideal MIS diode. Measured with the respect to the intrinsic Fermi level EI, which is shown in the figure. That means if we measure the voltage with respect to the Fermi level, then all these things discussed in our previous video. At the semiconductor surface we have phi is equal to phi s. Suppose we take the potential, that is a phi, but this potential here we consider at the semiconductor surface, so we denote it as a phi s, where phi s is called as the surface potential. The electron and hole concentration are given by all these conditions or all these situation. Here we consider at the semiconductor surface, so here we have to take the potential which is at the semiconductor surface, and which is the phi s, sorry not phi s, phi s, right? Concentration are given below. Here NP is the NP0 exponential Q psi divided by KT is equal to NP0 exponential beta psi. Here is the psi, that is NP is for which is the concentration for the electron, that is Np0 exponential q psi divided by kT. KT is the thermal energy, q is the charge, psi is the potential, Np0 is the original electron concentration. And also for beta we can write here 1 over kT. So we get the electron concentration. Similarly, hole concentration is the Pp is equal to P0 exponential minus q psi divided by kT is equal to Pp0 exponential minus beta psi. This is the expression for the hole concentration. But this expression we have to write at the surface of the semiconductor material. So here we need to just replace psi by psi s, because here we consider the all these phenomena at the surface. So just replace psi by psi s, then we get above equation, that is Np is equal to Np0 exponential q psi s divided by kT is equal to Np0 exponential beta psi s. And again for the hole, that is Pp is equal to Pp0 exponential minus q psi s divided by kT is equal to Pp0 exponential minus beta psi s. These all are the electron and hole concentrations. Now we have to find the expression for the space charge region. So this is not sufficient. So we have to consider the different cases like a Poisson equation. The potential psi as a function of a distance can be obtained by using the one-dimensional Poisson equation as given below. We know that generally the Poisson equation in electrodynamics, that is del square psi is equal to minus rho divided by epsilon 0, and here we consider all this situation at the semiconductor surface. So we take according to that, that is a Poisson equation which is for 1D, because our potential is at surface and which is only the function of the distance, that is x. So dabba 2 psi by dabba x square is equal to minus rho of x divided by epsilon s, where epsilon s is for the semiconductor. So here we take suffix s. Rho of x be the total charge density and is given by rho of x is equal to q into nd plus minus na minus plus pp minus np, where pp is the concentration of hole, np is the concentration of electron. Due to electron there is a negative sign to the np. Again na is the acceptor concentration and nd is the donor concentration. For na here we take minus sign, and for nd here we take plus sign, because after donating there is a losing of the electron and plus sign get it on because deficiency of the electron. So here we take nd plus and na minus, and for the na minus there is a gaining of the electron, so the negative sign for the na, so na minus. So here is the density. We know that density is nothing but the q into electron or the carrier concentration. According to concept of charge neutrality at the surface of the semiconductor, we can write. We know that in the semiconductor the overall charge at the surface is the 0, that is there are the equal number of the positive charges and the negative charges. So here we write rho of x is equal to 0, that is q into in bracket nd plus minus na minus plus pp minus np is equal to 0. This is the expression for density or the total charge density. But at the equilibrium we can write, that means at the equilibrium there are again equal number of holes and electrons and also their corresponding donor and acceptor concentration. So nd plus minus na minus is equal to np0 minus pp0. By using values of pp and p, we can write d2 psi by dx square as follows. That is we have the equation, that is for d2 psi by dx square is equal to minus rho of x divided by epsilon x. But from above equation we have the value of rho of x, then substitute the value of rho of x, then we get d2 psi by dx square is equal to minus q nd plus minus na minus plus pp minus np divided by epsilon x, or simply we can write in terms of np0 and pp0, that is q into np0 minus pp0 plus p P minus NP divided by epsilon s. So this is the required equation for the dabba 2 psi by dabba x square in terms of NP0, PP0, PP and NP. Now after collecting the term, that is the term of the PP0 and NP0, here we get minus q NP0 minus PP0 plus PP0 exponential minus beta psi minus PP0 exponential beta psi divided by epsilon s. Here in this step we substitute the value of NP0, NP and PP from the previous equation, that is the from here we have the value of NP and PP. After we substituting the value of NP and PP, we get this equation. Now collect the term of PP0 and NP0. So dabba 2 psi by dabba x square is equal to minus q. The term of PP0 is the exponential minus beta psi minus 1 minus NP0, that is the term of the NP0 exponential beta psi minus 1 divided by epsilon s. So this is the dabba 2 psi by dabba x square when we substitute the value of NP0 and PP and NP. Again we know that the electric field is the negative gradient of the potential. Here we have the potential, that is a psi, and which is the function of x. So here we can write epsilon is equal to minus dabba psi by dabba x. Also for the bulk surface we can write, if we have the semiconductor surface and which is the bulk surface, then we need to take the integration. So epsilon is equal to 0 to dabba psi by dabba x, or for the dabba 2 psi by dabba x square we can write dabba psi by dabba x into dabba psi by dabba x, and here derivative and integration with get cancelled with each other and our remaining terms as it is. So here minus q divided by epsilon s integration from 0 to psi PP0 exponential minus of beta psi minus 1 bracket complete minus NP0 in bracket exponential beta psi minus 1 into d psi. So this is the integrated term. Now after solving this term we get the value of epsilon square, because dabba psi by dabba x into dabba psi by dabba x is nothing but the dabba 2 psi by dabba x square, and which is nothing but the epsilon square. So epsilon square is equal to 2 kt by q whole bracket square into q pp0 into beta divided by 2 epsilon s in bracket exponential of minus beta psi plus beta psi minus 1 plus np0 divided by pp0 into in bracket exponential minus exponential beta psi minus 1. So this is the required equation after integrating the above equation. Now we have to define the one term here, that is a Debye length, and which is denoted by LD, which is the extrinsic Debye length, and which is for the whole. So LD is equal to under root KT epsilon s divided by PP0 Q square, but we know that KT is nothing but the beta, so here we can write under root epsilon s divided by PP0 Q square beta. So using the value of LD and defining another function, we can write the epsilon. So define the function such that let us define the function as f of beta phi np0 by pp0. That is a function, f is nothing but the function of beta psi and np0 by pp0, which is equal to exponential minus beta psi plus beta psi minus 1 plus np0 divided by pp0 into exponential beta psi minus 1 raised to whole bracket, that is a half. So this is the term which is present in our equation, that is the equation we get after integration. So here we define the function. Now we have to write the equation for epsilon. So substitute the value of this function and the value of LD in the epsilon square equation and take square root, then we get the epsilon such that epsilon is equal to minus dabba psi by dabba x, which is equal to plus minus sign. Why plus minus sign? Because here we take square root, so and adjusting the term, that is LD, and the function, that is f. So here we get plus minus root 2 kt divided by qld into f of beta psi np0 and np0 divided by pp0. So this is the required epsilon, that is the electric field at the surface of the semiconductor. Now from that we have to find the space charge per unit area of the semiconductor or the for the MIS diode. So space charge per unit area required to produce this electric field is given by Qs is equal to minus epsilon s into epsilon, and which is nothing but the just multiply by minus epsilon s. So here there is a reverse sign, that is a minus plus root kt divided by QLD as it is, and the multiplied term, that is a epsilon s into function again as it is, that is a f of beta phi np0 divided by pp0. So this is the required equation for the space charge per unit area required to produce the electric field, that is a epsilon, and this is for the MIS diode, but generally it is a ideal MIS diode. So this is the required expression for the space charge in a ideal metal insulator semiconductor diode. So here is the expression. Now in this way we have covered all theory about the metal insulator semiconductor diode and also for the impact diode. So in this way we have covered all topics of this chapter, that is a fourth chapter, metal and metal insulator semiconductor devices. So with this topic we finish this chapter. So in our next lecture we will discuss with the next chapter, that is a remaining chapter is the third chapter. So in our next video we will continue with the third chapter.